Hello, everyone. Thanks for joining. Welcome to this interactive session on machine learning. So we'll start in a few minutes, but before that, um, we'll start in a few minutes. But before that, please click on the link to the Jupyter Hub server in your email. It will redirect you to the Jupyter Hub server, and you'll be prompted for a login. So if you have already logged in for the previous session, you can use your old user ID and password. If you're logging in for the first time, then the password you give it for the first time will be your password. Will be your password. On clicking that link, you should have downloaded things from a GitHub repository. And that GitHub repository contains some data and some skeleton code that is going to help you get started if you want to follow along with this interactive session. Is on. Okay. So we're officially starting now. So the first thing you should see after logging in is this screen here, and you should be inside this folder, the Coding Club Talks folder. And there are two subfolders, and if you open the second folder, the perceptron folder, there is a Python notebook. So you can just open this Python notebook, and here so I have written some skeleton code, so you don't have to write everything. So the housekeeping is done for you. The only thing you have to write is the important stuff. So we'll get to that. So I'll write the entire code, and if you want to follow along, you just have to replace these nones by whatever you think is appropriate or whatever you learn. Okay. So okay, so we are going to start now. So first thing, so we are trying to do machine learning, right? So machine learning, essentially, it is just a fancy name for having a function and tuning the parameters of that function in order to do your job. So if you want to classify something, then you have a function that looks at your input, whatever that is. So if the function takes in an image, let's say, and tells you if it's a cat or not a cat. Okay, so that is all there is to it. So if you keep this image in mind, it should help demystify things a little bit. So before we start writing the actual code, so I'll talk a little bit about the artificial neurons. Okay. So artificial neurons. So, okay. So here I have made a very crude drawing of a neuron. So this you find in most biology textbooks. And by its side, I have drawn an even cruder representation of that neuron. So what this looks like, if you squint at it, is that it is taking some inputs here. So that those inputs usually are impulses, electrical impulses in your brain. But here we'll say that those inputs are numbers. So some numbers x1, x2, x3, and x4. And based on those numbers, this gives some output. Okay, that output we're going to call y. And this output then is fed into maybe some other neuron or some other to some other neuron, which may be getting its inputs from other neurons, etc. Okay, so today for the first talk, we are going to try to demystify this thing, okay, this structure. So now I'm going to warn you, so this is going to be a little bit math heavy, okay, but don't worry. So for writing the code itself, you don't need an understanding of the mathematics, but it is always good to know what is happening behind the scenes. Okay, so we are going to, okay, so for this neuron, so how exactly it takes in these inputs and produces an output. So let's take a quick look at that. Okay, so let's see. I have my neuron here and I have inputs. Okay, inputs, 4 inputs for now. So x1, x2, x3, and x4. Okay, and this is producing one output. Y. So one very easy way to define this y is to just add the 4 inputs. Okay, so we have x1 plus x2 plus x3 plus x4. Okay, but this again, this is very blunt. Okay, so we cannot really do anything with it. So if you just have a neuron which just adds the 4 inputs, it's not very useful and not very interesting. So what we do is we say that all of these inputs, they have different importances, right? And we assign certain weights to each of these inputs. So weight 1, W2, W3, W4. So these weights determine how important these inputs are. Okay, so if this W1 is a large non-zero number, then the X1 input is important for this neuron. Okay, so I'll just multiply. So the way to encode that in mathematics is to multiply the input by its corresponding weight. Okay, so I have W1 X1, W2 X2, W3 X3, and W4 X4. So this is slightly better because I have some parameters here, W1, W2, W3, and W4, which can help me, which can make the action of this neuron more, let's say, interesting, right? So it's now doing something more interesting, and we can also add a constant number. Okay, so these W's are weights, and we call this constant the bias. Okay. So now the goal of machine learning is so what we'll do today is we'll have a certain thing that we want to classify in 2 classes. So, and what we want this neuron to do is take that input and give out the correct output. And in order to do that, we'll write code to find these weights and biases, these parameters of the model. So now I'm using a bit of machine learning jargon. So these parameters, we want to find the values of these parameters such that my neural network, or just a single neuron in this case, gives the correct output given my input. Okay. So before going further, I'm going to just do one more little thing. It's that, so here I'm going to identify this x1, x2, x3, and x4 as a vector x. So x is a vector and its components are x1, x2, x3, and x4. And I'm going to define a weight vector w, whose components are w1, w2, w3, and w4. Okay. And the bias b is just a number. Okay. So now I can write this expression a little bit more compactly as w dot x. Okay, so this quantity here, it looks like a dot product. So I'm writing that plus a number b. Okay, so I have this. Now, given this, let's try to write some kind of data structure in Python that can capture some of these things. Okay, so I'm going to go back to the Jupyter notebook. And here, so first thing I'm going to do is import NumPy as np and import matplotlib.pyplot as plt. So we'll use the Python library NumPy for our computations because it makes things like vector algebra very fast. Okay, compared to if you're just using lists and using for loops inside Python. Okay, so this is just standard stuff. And the second thing we want to do is we want to write some kind of data structure that can represent our neuron. Okay, so you see I have given the name perceptron to it. So this artificial neuron which takes an input and gives some output, it's called a perceptron. Okay, so what I'm going to do is I'm going to define a class. So a class is basically a way to keep different kinds of things together. So we want to keep the weights of the neuron and weights of the perceptron and the bias of the perceptron together. Okay, so just to make writing code easier and make our code look pretty, so I'll write a perceptron class, and inside this class I have so when this class starts, so I have to define some initialization function self, and it's going to take as an input, let's say, how many inputs does the neuron take? Okay, let's say that that is a parameter that we can vary. So in size, so this is, and here again, so here self dot w is equal to, so w is the weight vector, and this vector I'm going to just, okay, let's say np dot zeros 1 comma in size. Okay, so this creates a row vector of size of dimension in size. Okay, and the other thing is self dot b, the bias. I'm going to put that equal to 1 for now. Okay, I can also put that equal to a random value which is just generated every time, but for now I'm not going to do that. I'm just going to write 1. Okay, now I also want to have this in size be a parameter of the perceptron or an attribute of the perceptron in size. Okay, so here the Python class, so I'm going to just run this first, and if I now create a new cell and write p is equal to perceptron, let's say what on now as an argument I have to give it the size of the input. Okay, so let's say I want an input of 4, input size of 4, and if I run this now, okay, cannot interpret. Okay, so here np dot zeros, this function, it takes a tuple instead of, this is just 2 arguments, it takes a tuple as its input. So this tuple gives you the size, gives you the shape of the NumPy array. So the NumPy array is a row vector, so that's why I'm writing 1 comma in size instead of just in size, and that should fix this error. Okay. Now this perceptron has been created, and I can also print it. So, but this is not very interesting. I mean, it is interesting in a certain sense, but it's not useful. It just gives you the address of the memory where this perceptron has been saved. So, what I'm going to just ignore it for now, and you'll have to trust me that this perceptron as defined it works. So, if, for example, if I write p dot w, then I get an array. So, a row vector of zeros. And similarly, if I write p dot b, I get 1, so which is the value of p, and p dot in size gives me the size of the input vector. Okay. So all this done. So now I have created a data structure. Now what does this data structure do? Now what I want to do is I want to apply this neuron, okay, apply the action of this neuron to my input. Okay. So let's go back to the notebook here. So here y, so this is the output. This is obtained by applying some action. So applying, so computing the dot product of w with x and adding a constant b. So this is how we are for now defining the action of our perceptron. So we want to write this into the Python code. Okay. So and we want to write this as a method of the class. So I'll write a class called apply. Okay. Which is going to take self. So self means the class itself. And also I'll take the vector. Okay, so the vector x, which should have size in size. Okay, so the dimension should be the value stored in the variable in size. And now I can compute the dot product, np dot of w with x and add the bias b. Okay, so this is just, I have translated what I have written earlier into Python code. Now I'll return that. Okay, so now let's try that too. Okay, so this perceptron has been created here. Now I can create some input vector x, just randomly initializing random dot rand n. Input size should be 4 because we have said that the perceptron takes an input of size 4, and we can apply this perceptron on this vector to get some output. Okay, does not have an attribute apply. Okay, w is not defined, so this should be self dot w, and this should be self dot b. So the reason I saw this error is because you have to tell what this w is. So just w, it's not an argument to the function. So this w is contained inside the self. Okay, and so I have to access it by using this dot notation. And now this should hopefully fix things. I have to run this cell first. Now, okay. So now this is giving an output of 1. So why is this giving an out? So now this output of 1, this should not be unexpected because the W matrix is entirely 0. So this dot product will give me 0. And this value of B, I initialized it to 1. So the output is 1. So it's not really surprising. Now there's another thing we want to do. So let's think in terms of our actual task now. Okay, so the actual task here is, let's say we are doing some kind of a binary classification. So we have something. Okay, let's say we have pictures, and we have cat pictures, and we have no cat pictures. Okay, so what we want to do is I want to feed the picture. So this picture, it goes inside a neural network, and the output should be something that tells me if it's a cat picture or if it's not a cat picture. So let's say that the neural network gives me 1 if it's a cat picture and 0 if it's a not a cat picture. Okay, so just so now so the takeaway should be that I want this value, this y, to be squished to some number inside the interval 0 and 1. Okay, and if I have that, then what I can do is that then I can round it down or round it up. And if it's rounded down to 0, then I'll say that it's not a cat picture. And if it's rounded up to 1, then I can say that it is a cat picture. Okay, so now how we'll tell the neural network to optimize for this. So it always gives 1 when it's a cat picture and always gives 0 when it's not a cat picture. That is exactly the process of gradient descent. Okay, which we'll start very soon. So now I have applied it. Now what I want to do is I want to define the activation function. Okay, the activation function here I'll call the sigmoid function. Sigmoid, which takes an argument, and the output is return 1 divided by 1 plus e dot exponential of minus z. Okay, so this is the sigmoid function, and what this function looks like I'll tell you in a bit. But the thing is that this sigmoid essentially squishes whatever input you give it to some value between 0 and 1. So sigmoid activation, sigmoid. So sigmoid is going to look something like this. So this is my x-axis and this is my y-axis. Y-axis is sigmoid of x. Then this graph is going to look something like this. Well, not really. So this is 1 and this is 0. So if I get a very large x value, I'll get an output very close to 1. And if I get a very negative large x value, I'll get a value very close to 0. Okay. So you can plot it in, let's say, Desmos and see that this is what this function should be shifted here. Okay. It should be more like this, but you can check that this is what the function looks like. Okay, and the motivation for doing that is to squish my output into some small interval between 0 and 1. So now for that, I'll define another function, which I'll call predict in this case, because using this function, we are going to be able to tell if it's a cat or not a cat. And this is just going to be returning, we are going to first apply sigmoid to self dot apply x. Okay, so where w dot x plus b, that is self dot apply, and we're applying sigmoid to that, and then finally we're going to round it up or round it down. So I'll write that now. So rounded up or rounded down. So that's there, and so now this is starting to look like something we can use. But the only problem is that given any input, the output is not correct. Okay, the output is basically garbage. So, and it depends very crucially on what these inputs were assigned to be. And now we are going to want to look for a method to optimize for these values. Okay, so we want to write an algorithm that finds some w vector and b some number that makes our perceptron do what we want it to do. Okay, so the way to do that, so that algorithm which we are going to talk about now is called gradient descent. Okay, now what gradient descent is essentially is that so now we want a measure of how well our neural network is doing, right? So now what we're going to do is, let's say I have some data set. Okay, I have some x values and some y values. Okay, my x is my data or the input, and y is an output. And in our case, the output is just a number between 0 and 1. Or it's a number, rather, it's either 0 or 1, because that's what our network is predicting. Now, what we want to do is we want to have a measure of how well our neural network is doing. So what we'll do is we'll define the action of a neural network, f of x, as this sigmoid function applied on w dot x plus b. Okay. And we want to compute something, a quantity like c, which I'll write to be half of f of x minus y squared. Okay. So this f of x is what our output is, and this y is what our output should have been. Okay. And we are taking the difference and squaring that. So the larger this value is, the worse our neural network is doing. And the smaller this value is, the better this neural network is doing. Okay. So we want to minimize this value. Okay. This value correctly is called the cost function. Okay. And this is called the mean squared cost function because we are using a square. There are different kinds of square cost functions which we'll cover in tomorrow's session. But for today, we are going to work with this because we are writing everything from scratch. So it's a little easier to have this C. Okay. So now now I'm going to define a quantity called the activation. Okay. Which is just this. So nothing fancy. So instead of having to write this f of x, I want to write a nice a. So that is my activation. And so why it's quite easy to see why it's called an activation. We are computing our we are doing some linear algebra, and then we are finding out its activation by using this function sigma, and then that gives me a. And now this cost function therefore is just half a minus y squared. Okay, now this a depends on x, of course. It depends on w, the weight matrices. It depends on b. Okay. Now what I want to do is I want to think of what this C looks like, okay, as a graph. So let's say it only depended on one thing, okay. Then the function C would have looked something like this. Let's say it looks something like this, okay. It does not have to have a minima, but just for the sake of our own sanity, we want it to have a minima, okay. And let's say that this is a parameter. Let's say that our network for the moment has just one weight, okay, and it has no bias. So it's just taking an input, it's multiplying it by something and just giving an output. And I want to find a value of w such that this cost function C is minimized. So I want my network to do better. I want the cost to be minimized. Therefore, I want to minimize this C with respect to w, okay. So when we are starting out, we are just randomly assigning these w values. For our case, we are just putting it to be equal to 0. And from here, I want to somehow get here. Okay. So what I can do is that here I see that in order to get to the minima, I can look at where the slope is downwards, right? So where the function is sloping towards. So if you know a derivative, that is exactly what a derivative is. So this gives me a measure of the slope. So if it's sloping this, side, or if it's sloping the upwards. So here it's sloping downwards, and therefore I want to go right. Okay, so this w value, I want to move w rightwards. Okay, so my w should move to w plus delta. Okay, because I want to go rightwards. Now, I'll just create a new page here. So now this delta value is positive. Okay, positive. Now what I want to do is I'll write w is equal to w minus some constant eta, some small constant, and this derivative. So I have put this minus sign here because this dc by dw, this is going to be negative, right? Because the function is sloping downwards here. It's going to be negative. And I want my delta value to be positive. Therefore, I have stuck in this minus sign here. And this holds quite generally. So if you can check for yourself that if I were to start from here, then my derivative would have been positive, but I would have wanted to go in the opposite direction. So again, I would have had this minus sign here. Now, but so this is all well and good, but the only problem is that C does not depend on W. It depends on W1, W2, W3, W4. It's a multi-variable function. So now the case for that too is quite straightforward. So the ith component of W is equal to the ith component of W minus eta and the partial derivative. So instead of the total derivative, I have a partial derivative with respect to W, and the same thing with respect to B. So B is just one number, so it's easier. So B minus eta del C over del B. Okay, this eta is a small constant. It's a positive constant. And it's called the learning rate. Learning rate. Okay. So now our job now is to compute these partial derivatives and carry this operation out however many times is necessary. Okay. So in order to compute this partial derivatives, I'm just going to rewrite the loss function here once again. Of f of x, or instead of f of x, let's write a minus y squared. Now del C by del B is just half 2 times a minus y del A by del B. Okay, here I've just used the chain rule. So first I've differentiated this, so this 2 comes out, this 2 and the half cancel, and then I have a derivative of A with respect to B. Now, I recall that A is written as sigma W dot x plus B, and this quantity, again, we have written a function for this quantity. It's called apply. This quantity, not just for not having to write it again and again, I'll write it as Z. And the derivative of A with respect to B then is, again, I'll use the chain rule. So sigma prime, the derivative of sigma with respect to Z at Z, then del Z by del B. Now, if you look at Z, this quantity does not depend on B. So the only B is here. So this will just give me 1. Okay. And therefore, I have my first important equation of the day. Del C by del B equals, what was it? A minus y sigma prime Z. Okay. Now this is something. Now I'll do the same thing for W's, but for W's, this del Z by del Wj, that's not going to be 1. It's going to be some constant, right? Now for that, again, I'll do a similar, so I'll just put a box in this. Now again, so I'll proceed similarly, del C by del Wj. Now I'm differentiating with the jth component of W. This again is A minus y del A by del Wj. Now this del A by del Wj, like before, is going to be, I'll just write A minus y first, sigma prime Z del A by del Wj. That's just going to give me, now I have del Z by del Wj, and Z is the sum over J of Wjx J plus B. So now if I'm differentiating with respect to the jth component, the xj is going to come out. Okay, all right, xj here. Now this is the second equation that we're going to use in order to train our network. And when we're training a network, we'll usually work with some data. Okay, so for the data, so data is going to be something like x comma y. This x is going to be a vector. Okay, I'm just repeating it again because it is very important. And this y is just going to be some number. Okay, it's going to be either 0 or it's going to be 1. All right. So now here, what we want to do is we want to update the value of W and the value of B. So these are to be updated based on the entire data. So just computing a single data point, that is not going to give me an idea of what the rest of the data is doing. Okay. So what I'm going to do is I'm going to compute such derivatives at each of these data points. Okay. So now remember, when I have written these derivatives here, I have used Z, and this Z and this Z here, these depend on X, and X is again explicitly here, and Y of course is again explicitly here. So these things depend on X and Y. So what I want to be doing is, just instead of doing Wj transform to Wj minus eta del C by del Wj, what I want is that, so now this C, it depends on the data point X comma Y. Now, what I want to do is, instead of just doing this transformation, I want to do the following. Wj goes to eta sum over all data points, right? So X comma Y, and now del C X comma Y del Wj. Okay, so now this has been a lot of math. So I'm just going to give everyone a breather for 2 minutes before we convert this math to code. All right, so if you have any questions till now, you can either write in the chat box, or you can ask your volunteers on the Google Meet link. Okay, so just I'll be back in 2 minutes. Okay, so we left at the following two equations, which I wrote down, which which I wrote down, which will help us to train our model. So quote unquote train. So we are going to start writing the code now. So we want to convert this bunch of math into some code. Okay, so for that, I'll switch back to the Jupyter lab. And here, now first I want to write a function that will compute the gradient. Okay, so like we talked about gradient, and let's say that it's going to take some batch of some data. Okay, so not just a single data point, it's going to take multiple data points to create to compute the gradient. Okay, now it's okay. Now I'll just write, now gradient, usually in math we write nabla, so I'll write nabla b and nabla w, and I'll initialize these to zero matrices. Okay, so 0 and np dot 0 is self w shape. Okay, so this is a zero matrix, which is the shape of the weight. Okay, so I'm sorry for calling these matrices. These are actually vectors, right? So now the this w dot shape is going to be nothing but this 1 comma in size, and b we know is just a number, so we are just initializing it to 0. Now what we want to do is we want to iterate over the batch of data. Okay, and we're going to we want to write the expression for gradient. First we'll compute the z self dot apply x, and next we want the activation, so I'll just apply the sigmoid to z to get the activation a. Now I want to write db. Okay, so db is this guy here. So this dc by db is, so this del c by del b, this is the variable db, and this involves a minus y, which are quantities we know, and the derivative of sigma, the activation function, applied to z. So we want to write now, so first thing we need to, so first we'll write this, and second we'll write the derivative of the sigma function. Now db is equal to a wait a minute, a minus y sigmoid of z. Z we have defined 2 lines above, and we want the derivative. And to get the derivative, I'm going to extend this function we have defined here. Okay. Now diff is equal to false by default. And now I want to, so now you can compute the derivative, but I'll just write it here. Okay. So I'll make this quantity s, and if the diff flag is there, then we want to return the derivative, which is s star 1 minus s. Otherwise, we'll just return s. Okay, so this s is just nothing but our earlier, the sigmoid function. And this derivative, I'm not going to go into it because, again, it's just a bunch of math, a bunch of symbol pushing. It does not add anything to the understanding. Okay, so now I have this, I'm returning. So now my sigmoid function is equipped to handle derivatives 2. Okay, so now I have this line here. Now I can write dw now. dw, again, we go back to the equation here. So now if we look at this quantity, this is nothing but db, right? And we're just multiplying it. So this is db is going to be a number because a is a number, y is a number, sigma prime z is a number. And this xj, we are just going to, so this kind of looks like a just a scalar multiplication, right? We're multiplying each component of the vector x by a scalar, right? So that is what we'll do here. So dw is the scalar db times x. Okay. Now again, so like I mentioned, I want to sum over all these data points, right? So at every data point, I want to compute the gradient, which is dB and dW here. And I want to sum over all of this. And summing over all of this, I'll just, now I'll use the variables I defined earlier, dB and nabla w updated, changed by dW. Okay. So now this is going to compute this quantity here, which I have written. So where is it? So this quantity here, we have computed this quantity. Okay, for Wj and also for Bj, for B, not J, because we only have a single number. Eta summed over all data points and something. Okay, so we have those quantities. So we're just going to return it. Return nabla B nabla W. Okay, so now that computes our gradient. Now we want to use this gradient to descent. Okay, so to find a maxima. So now we can define a train function, right? So now we're training the neural network. So now again, so I said this earlier, but I'll say this again, that training is nothing but finding a set of values for our parameters, so for our weights and biases, such that this neural network behaves in the way we want. Okay. So an analogy, very close analogy actually, would be curve fitting, which everyone does. Okay, so you want to do a straight line fitting, or if you want to do a polynomial fitting. So you start with a function in which you have the functional form and the parameters, so the coefficients of the polynomial are undetermined. And what you want to do is you want to find a set of parameters which fits your curve. Okay, so here you can this is just a higher dimensional analog of that. So you have a curve, you have a quote unquote curve, which takes in all of these values, so x1, x2, x3, and x4. And the parameters are there. So parameters are w and b. And you want to optimize this w and b such that your curve is fitted, right? So now that curve is defined by your data set. So the x values and the y values. Okay. So now train self. Again, I'll take a batch of data and I'm going to write db. So the value I want to change b by, and dw. So db is going to be db dw equals gradient self dot gradient over this batch of data, and I'll update the w and b values. So w is equal to w minus the eta. So eta is called the learning rate. I'll write the whole thing here. Learning rate times dw, and self dot b is learning rate times db. Okay, so this is, we're updating our parameters here. Okay, now however, so this just goes through the data set once and it updates the parameter, but usually this is not enough. You want to do this whole process a number of times, right? So now each of those times is called an epoch. So I'll write a new thing, I'll add a new parameter here, an epoch, and I'll write, and I'll iterate over all the epochs. So E in range epochs. And now for every epoch, I'm going to update my variables. Okay. However, so now just to add a little, so now for now, what is happening is that you're given a batch of data and you're iterating over that batch of data, in exactly the same order every time. Okay, so which is not good, because you, in a sense, what you're doing, you're just repeating the same process over and over again. And now what can happen is that the choice of your parameters W and B, they can depend on the order of the data, right? Which we don't want, because the order, unless you are doing something that requires that, but usually the order in which we are feeding it the data is not important. So we want to shuffle the entire data set every time, right? So now what I'll do here is I'll do an np dot random dot shuffle. I'll shuffle the batch. Okay, so what this is going to do is this is going to shuffle the batch in place, right? So the batch variable itself is being modified and it returns nothing. And now I have this. And so this, essentially, this is, our task is done. Okay, so just to uh, have it print nice messages to us while it's training. I'll just write a status message: training complete, training for epoch complete. Epoch is e plus 1 because indices start from 0. And this should do my training. Okay. However, so now if it's it's updating the parameters, but right now we have no way of finding out how well the network is doing or how well this perceptron is doing at its job, right? So in order to do that, so I'll just run this cell once. So in order to do that, there are two things. There is the accuracy and there is something called the loss. Okay. So loss we have already seen here, which loss is the quantity which we wanted to minimize for. Cost is the quantity which we wanted to minimize for. So this is the cost. So I want to compute this, okay, but not exactly this. I want to compute this over all data sets. So I want to sum over all data points. And I want to compute that cost. Okay, so this is something I want to keep track of at each step of the training. So I'll just write a function to do that. Where are we? So here I'll define cost self. It will take the entire batch as, and what I'll do is I'll compute the sum of half self. Now what we are doing is self dot predict x minus y for x, y in batch. Okay, so this should work. Okay, so I should have squared it here, right? So we have just written what we had. So we have written the equation in this form. Okay, so just so this entire thing is not dependent on the size of our data set, we'll average it over all data points. Okay, so in the end we're dividing by the size of the data set. Okay, we're calculating the mean now. Now once we have that, so we can also print, in addition to the status message that training has been completed, we can also print the loss, right? Complete dot something happened format e plus 1. Here new line loss or rather cost. We can now mention the cost function here, which is self dot r. Right, instead of writing this here, I can find the cost c is equal to self dot cost and the batch. Batch cost. Okay. So now also another thing we are maybe interested in is the accuracy. Okay. Is the accuracy. So how well, so given the data set, how many cat pictures is it classifying correctly? Okay. So I also want to keep track of that during the training. Self, again, I want an entire batch to do this. Forgot a return statement here. Now accuracy is the sum of self dot predict x equals y. So the x value is equal to the y value in our batch, and we want to divide this by the length of the batch. Okay, so this will give me the fraction of cat images that were classified correctly. Okay, so if I'll just run this, oh, wait a minute. I'll just run this cell once to make sure there are no obvious syntax errors. There are not, which is good. Now, so in addition to having the cost here, I can also have the loss, the accuracy. Accuracy. Write this A here, A, and self dot accuracy. Okay, so that is nice. So now this, in a sense, completes our code for the perceptron. Okay, so now all that is left to do is try this out on a real data set. Okay, so this is done. It runs. Good. Now this doesn't run. What we are going, I mean, this does. So this is our perceptron, right? Perceptron definition. And now we want to just load some data just to play with it, right? So loading data. So if you're following along using that Python notebook, which is in the GitHub repo, this part should already be written down for you, right? So the data and the data file should have been should be in the working directory. I'll just run this cluster. Okay, does not work. It does not work because it's not in my working directory. Paste. You should not have to do this, because if you have cloned that Git repository, then the files are in the same directory. Right, so now this does work. Now what I want to do is I want to I'll just plot this. So after plotting it, it's easier to explain what this data set is. Okay. Right. So this is our data set. All right. So our data set is, I'll just, so cluster data. So our data set is a set of points. Okay. So it's a list which contains x comma y value. So the x value is actually a two-dimensional vector. So it's x component of a vector and y component of a vector, and the y value here is its classification. So if it belongs to this cluster of points here, or if it belongs to this cluster of points here. Okay. So this is our data set, right? And it's pretty straightforward, and it's about 400-500 samples. So now what we want to do is we want our perceptron to be able, so given a point, so given the coordinates of a point, we want our perceptron to be able to tell if it belongs to this cluster here, the red cluster or the blue cluster. Okay. So this is our training data. Now what we're going to do is we're going to create a perceptron. Okay. So perceptron, I'll just call it P. Okay. It's perceptron. Its input is two-dimensional vectors because the x, it's just x component comma y component. So it's a two-dimensional vector. So that is what I'm taking as input. And yeah, so I'm just creating a perceptron using that. And also I just for fun, I want to calculate the accuracy of this perceptron before we have done any training. So remember, this is just randomly initialized. Okay. So accuracy is accuracy on this cluster data. So this batch of data. Okay. So I've passed it the entire thing. Let's see. So it's you see it's 50% accuracy, right? Which means that it's just randomly guessing and it's getting it right 50% of the times. Okay, that's one way to think about it. All right. So now we want to train this. Okay, so in order to train it, what we're going to do is we're going to p.train. Remember, we have written this function train here, right? And let's see what inputs it takes. It takes batch. So which batch of data we want to train it over. And it takes input as input of epoch. So how many epochs we want to take it, train it. So p.train, I'll put cluster data. And okay, so there is one thing here that we have not taken as argument to this train function. So learning rate here, it would have given an undefined variable error. So, but we have caught that. And we also need learning rate. We also need to pass learning rate to the train. So learning rate, it can be some small quantity. So again, let's look at it. So batch of data, learning rate, epochs. So batch of data is the entire thing, the cluster data. I also want the learning rate, let's say 0.1. And epochs, let's say I want to train it for 10 epochs. Okay, let's run it. 3 positional arguments, but 4 were given. Let's see what went wrong. What went wrong is that we didn't run this cell. Now this should work. Okay, I did not run this cell. Now it should work. Okay, so you see, so from 50% accuracy, we have gone to 98% accuracy just in the first epoch. So the first time we are updating the weights, we are getting to 98% accuracy. And you see the loss, it keeps on decreasing. So it starts from 0.006, goes to 0.005, all the way to 4 in the 10th epoch. And the accuracy is 99.2%. So it can classify with 99.2% how it can classify with 99.2% accuracy which cluster the point belongs to. Okay, just to appreciate what this network is doing, so I'm just going to run this, and then I'm going to so I want to plot what the perceptron here, which has been initialized randomly, thinks each point is, right? So which cluster each point belongs to. So for that, I have some code here, which I'll just, okay, so I have this code here. I'll just write a code like that for x, y in cluster data. If p.predict x is equal to 0. So if the network thinks that it belongs to the cluster 0, I'm going to make a scatter plot of that point and color it blue like before. And otherwise, if it predicts that x, well, if it gives output 1, plt dot scatter unpack X color is equal to red. Okay. Okay. So you see, it was 50% accuracy because it was just assigning every point to cluster 1. Okay, which is not surprising. Again, remember when we worked that example in the beginning of the session. Because this W is 0 and B is 1, no matter what vector you give it, it will output 1. Okay, which means that no matter which set of x comma y point you give it, it is just going to give out 1. Okay, which means that it will color the point red. And now we can train this data, train this network. Okay, so the accuracy increases and this the cost goes down. Now I'll just copy this code from here and paste it after it has trained. And okay, so I don't want to do the training again. So I need a new cell. Wait, oops. I want a new tab. Does this work? No. Okay. Wait, what? Okay, so moment. Okay, so 99.2% accuracy. Paste the code. Run the code. This should be much closer to this here, this distribution. Okay, right. So you see, so it is doing a pretty good job. So it has understood that if it's given a point close to the coordinate -1 comma -1, it's going to go to category 1, and if it's a point closer to 1 comma 1, it's going to this category category 0, or I said that the other way around. Okay, so if the point is closer to -1 comma -1, it's going to category 0 and colored blue, and if it's closer to 1 comma 1, it's going to category 1 and it's going to be colored red. Okay, there are a few points it doesn't get, but you cannot fault the network or fault the neuron for it, because you see how just we did not tell this perceptron explicitly what points are, okay, and what coordinates are and what distances. So we did not tell it explicitly any of those things. We just threw some data at it, and we just asked it to figure out what's going on with it. And considering that, it's done a pretty good job. And the few points, so it's not 100% accurate. The few points it has missed, a human could have missed these 2 points easily, okay, any day. So this network, this single neuron, for this task, it's almost as good as human, okay, and it also does not take very long to train. So it attains 99.2% accuracy just after the first epoch of training. Okay, so that is the major part of the talk. Okay, that is mostly everything I wanted to cover today. Now, I just before closing remarks, I'm going to give another a breather of 5 minutes just to ask questions to your volunteers or post your questions in the chat uh, before my closing remarks. Okay. Okay. All right. So, so today we have seen what an individual perceptron is like. So just a single artificial neuron. Now, tomorrow, what we're going to see is how to create a network using these single neurons. Okay. So I'll make a pretty drawing here. So what we have seen here is a single neuron, right? This is a single neuron, takes inputs x1, 2, 3, 4, and it gives an output. And this is the model we've been using, right? But this is a very simple model. It cannot capture a lot of interesting things about your data. Okay, so the thing we did with it, it's about the most complicated thing you can do with a single neuron. However, if you connect a bunch of these neurons, right? So if I have a bunch of these neurons all connected together, it can do pretty amazing things. Okay. So all of these little guys are neurons, and every neuron is connected to every other neuron. Okay, by connection, I mean that the output of this neuron is an input to this second neuron. The output or the activation of this neuron is an input to this other neuron. Okay, and so on and so forth. Right, and this layer of neurons is now connected to the layers in front of it. So now what happens if you do something like this is that if you have an input here, so input, and this input, let's say for now, is just a vector. Okay, this input, it goes into each of these neurons. Okay, and each of these neurons have some activation, and that activation is fed into this second layer of neurons, and the activation of these neurons based on the activations of previous layer are fed forward into this deeper layer of neurons, right? So the activations here, look, are being fed forward. Okay, so the activation of this neuron affects this neuron, but the activation ahead doesn't affect what happens behind it. Okay, therefore something like this, it's called a feed forward network. Feed forward network, and it's the simplest kind of network, and it's the simplest kind of neural network that most people come across. And tomorrow, Spandan will use a feed forward network to classify handwritten digits. Okay, so if I write this number 6, so we'll write a neural network that takes this image as an input. How that happens, Spandan will tell you. And it tells you that this number is actually 6. Okay, so this is quite literally the first problem people, quite generally the first problem people come across when they do ML. And it is a problem we usually use to motivate why ML is important. Because if we want to explicitly write a code for why this number, how this drawing of a number, so how some pixels are associated to a number, it gets very hard very quickly. Okay, so for example, for the problem we saw today, the classifying it into clusters, you could have written explicitly a code for doing that. But for something like this or something like computer vision, you cannot do that. Okay, and since cats were promised in the invitation email, and I also mentioned cats a few times, I'll also say that once we have done this MNIST classification, doing so writing a similar neural network to classify whether something is a cat or not a cat, it's actually a very simple a very similar, an extremely similar neural network does the same thing. So that maybe again tomorrow Spandan will cover. Okay, so that is it. Thank you everyone who have stuck around for this long. Thank you everyone for attending. And yes, so that's it.